Welcome to the second development video of Scott's counter application. Now in this video we are going to focus on object detection using deep learning. Now for those who don't know, object detection is a process to detect and identify objects in an image or a video without human intervention. The objects could be anything. It could be an aeroplane, laptop, monitor, mouse, it could be anything. Okay. Now this is achieved by using deep learning algorithms. Now there are various deep learning algorithms. One of them is YOLO model, which we are going to use in our project. Okay. YOLO model is deep learning's powerful model specifically designed for detection of objects in an image or a video. It stands for you only look once, and it is quite fast and accurate. Okay, now to give you an example how YOLO actually works, show an image of a car to your brain and your brain will instantly recognizes it as a car, right? So same way this YOLO model works. You show him an image of a car and it will detect it, and using OpenCV code we will be able to draw the bounding boxes around the car and also label it. Okay, so there are two files associated with a YOLO model. First one is configuration file and second one is the weights file. Now before actually training a YOLO model, we have to first prepare this configuration file. This file contains all the neural network and layers information and how they connect. It also contains the type of image, whether it should be a black and white image or it should be a colorful image, and what are the resolution. All these information are considered before actually training a YOLO model. Okay. Now comes the weights file. This weights file is produced after the YOLO model is trained. Okay. It contains all the information that the YOLO model has learned. So we are going to use these two files in our code for the detection of our hands and faces. Okay. Now coming back to the development part, we are going to write a class to load the pre-trained face and hand detection models. Now what do I mean by pre-trained models? I already have models which are trained to detect our faces and hands in an image or a video. I'm not going to show you the process of training a YOLO model because it's quite a vast topic, but if you want me to show you the process, let me know in the comments. Okay. Now after that, we are going to write some methods in the same class to integrate these two models with the code that we wrote in our previous video. So by the end of this video, we will be able to detect our faces and hands in the live video coming through our camera. So let's get to the development part. So this is the code that we wrote in our previous video, and let me zoom in a bit here. And also we did not set up the interpreter last time, so we will go to the environment that we created, scripts, and we'll copy the path of this python.exe absolute path and add new interpreter. Select this and then okay. Yeah, it's being updated. Let's close this. Now we'll start with writing a class YOLO model and initialize a constructor which will take input parameters as CFG file path and and weights file path. We already discussed what are these files, right? CFG file and the weights file. So we'll create two variables, self dot CFG file path equals to CFG file path and weights file equals to weights file. Now we have to load the model using these files. We'll create a method load model and we are going to define a variable net equals to cv2 dot dnn dot read net from darknet, and this will take two arguments, cfg file and the weights file. So cfg self dot cfg file path comma self dot weights file path, and we will return this method. Now we are going to define one variable self dot net equals to self dot load model. Now we have loaded our model using the cfg file and the weights file. After this, we will pass the image coming through our camera to our model to detect the objects in it. Okay, so we will define a method called as detect objects, and this will contain the image as parameter. We cannot directly pass the image. We will first have to pre-process the image to make it compatible for our model to accept it as an input. Okay, so we'll create a variable called as blob, and cv2 dot dnn dot blob from image, and we'll pass this image here. We'll keep the scale factor as 1 divided by 255. We will give the mean 0, 0, 0. Swap RB will be true. Swap RB is swapping the RGB color to BGR. Okay, red, green, blue to blue, green, and red. Then we do not want to crop the image, so we'll keep it as false. We won't crop it, but we will resize the image. So like I said, every model is trained on a specific resolution, right? So your image could be of 1024 or 716 pixels of resolution, but the model could accept a resolution of 416 by 416. So we'll have to resize it, the original image. We'll define the height and width here, that is equal to 416, and width will also be 416. We'll pass the self dot height comma self dot width. Let me show you in the paint how it looks like. Suppose this is your original image. Okay, it could be of 716 or 1024 for example, or 1024 or 48 for example. Now what this code will do is, will convert your image into blob. First it will resize it. Okay, it will resize the image into 416 by 416 pixels, and this image will go as an input to our model. So we have converted this to this. We will set this blob as an input to our model. So self.net dot set input blob. Okay. Then now we have pre-processed the image. We have set the input to our model, the pre-processed image. Now in deep learning, every neural network gives us the prediction through its last layers. Okay, so we'll have to get the last layers names here to get the detections. So we'll define a method called as get layers name, and first we will get all the layers name using self.net dot get layers name, and we will filter out the last layers from this layers name. We will return a list layers name I minus 1 for I in self.net dot get unconnected out layers. Okay, So it will filter out this layers in list and get all the out layers in a list, and then we are returning it. Then we'll create a variable outs and self dot net dot forward. We'll call this get layers name method. So once we have done this, the model will detect all the objects in the image, and all the coordinates of the detection will be stored in this outs. Okay. So for example, this is your original image and this is your face, for example, and this is the pre-processed image. Okay, 416 by 416, and this is your face. Using this code, okay, model will detect it like this, detect our face like this. And you see this red box, these are nothing but the coordinates of the face in this 416 by 416 image. So all the coordinates are stored in this outs folder. So we'll have to loop this outs and get the coordinates. We will create a method called as post process, which will take input parameters as image and this outs. Like I said, we'll have to loop it. So we'll loop for out and outs, and this out will contain the list of detections. Okay, so for detection in out, now let me show you what this list actually looks like. So detection equals to a list. Now the first four coordinates, sorry, the first four elements will be the coordinates. For example, 45, 56, 67, just giving an example, 78. And after that there will be accuracy scores, which ranges from 0 to 1. So it could be 0 0.3, 0 0.7, 0 0.01. Okay. Just giving an example. Now we'll get all the scores in another list. So we'll define scores equals to detection. First four elements are the coordinates, rest are the scores. So scores will look something like this. Now why did I choose three scores here? These are basically the classes. Like if your model is trained on three classes, there will be three scores. If your model is trained on only one class, there will be only one score. Just giving an example. Okay, then we'll get the class ID np dot arithmex. Np is numpy. We are getting the maximum number out of these three ones, and we'll pass the scores here. So class ID would look like, since 0.7 is the maximum and its index position is 1. Okay, so the class ID will be 1. Now we will get the confidence accuracy equals to scores and then class ID. So confidence would look something like 0.7, since it is the maximum among these three. Okay, like with every detection, YOLO model provides us the confidence, how confident the model is with the detection it has made. Okay, so the higher the confidence is, the better the detection done by the model. Okay, so if confidence is greater than 0.5, now what this condition means is we are basically dropping all the weak detections done by the model. We will only consider the detections that are higher than 0.5, that is 50%. Okay, let's not define this hard code. We'll define the confidence threshold here. threshold equals to 0.5 and self dot confidence threshold equals to confidence threshold, and we will use this here, self dot confidence threshold. Now the model has done the detection in 416 by 416 pixels of image, right? We cannot use this red box here, so we will have to convert the coordinates, the red box coordinates, and make it compatible to this original image. Okay, so there are some formulae that we will have to use to convert these coordinates into our original image coordinates. So coming back to the code, so, we are getting the center x, center y, width, height, left and top. Okay, we'll have to define, let's call this as frame or image. We'll have to get the original image height and width first. Okay, so frame height equals to frame dot shape of 0, and frame width will be 1. Boxes comma confidences equals to this, and we will append the confidences here. Confidences dot append float of confidence, and in boxes we will store the boxes dot append a list of this left top with height, left comma top comma with comma height. In deep learning, there is a technique called as non-maximum suppression, and what it does is, suppose this is your image, okay, and this is your face, and what your model will do is it will create multiple instances of the same object. For example, it will detect once, it will create another instance, it will create another box as the detection. Okay, and there is one detection that it will make which will be better than the rest of the ones. So NMS technique will remove all the green ones, all the green detections, since we will only need one detection. So it will remove all the green ones and it will only keep the red ones. So non-maximum suppression technique compares the confidences of each boxes and keeps only the one with the highest score. Okay. So we'll have to make use of that as well. We'll create one variable, then cv2.dnn.nms boxes. We'll have to pass the boxes here, then confidences, then we'll have to pass the confidence threshold, and then the NMS threshold as well. We haven't defined it. Let's define the NMS threshold here. Equals to 0.5, 0.4. 0.4 is the ideal number. Self dot NMS threshold. Okay. Now we will loop the indices here. For I in indices, and we'll take each box here, boxes of I, and left equals to box of 0, width and height 0, 1, 2 and 3. Now we have the left and top. Okay, now we have the this we have this left and we have this top. Okay, now we'll have to calculate the right and bottom of this. So to do that, we will write equals to left plus width, then calculate the bottom as top plus height. Okay, and then we will create another, let's call as final boxes equals to until us, and then we will append the final boxes dot append top, left, right, bottom. Now we only have the coordinates, we haven't drawn any boxes yet. Okay, so we will draw it using the cv2 dot rectangle. We will pass the frame here, and in a tuple we will pass top. The coordinates basically we'll have to pass it to the cv2 dot rectangle method, so it could draw the box around the object. Top, left, bottom, right. Then we'll have to pass the color, so let's pass 0 comma 55 comma 255, and this will be the width of the box, how thick we want the box to be. So we'll keep it as 2, and we will return final boxes. Okay, so we are going to use this final boxes. No, wait, we haven't called this post process method yet, right? So we will create objects variable and call this self dot post process. We'll pass the image and the outs, and then we will return the objects. So we are going to integrate this YOLO model class in our classes course that we wrote previously, and we will call this detect objects method to get the coordinates of the objects as well as draw the bounding boxes around the object, and but we'll have to pass the image for this. So our YOLO model class is completed. We will now integrate this model in our class codes to detect our hands and faces. But first, let's rewind back and see what we have written in the class YOLO model. So we have initialized a constructor and passed the parameters safety file path, weights file path, confidence threshold, and NMS threshold. Then we are defining those here, and then we are loading the model. And once the model is loaded, we are detecting the objects. We are passing the image as a parameter, and we are pre-processing the image using this. We are setting up the input to our model, then we are getting the layers name and we are forwarding it. Actually we can remove this extra parenthesis. Then we have the post process method where we are taking the parameters as frame and outs contains all the detections. We are getting the original image height and width, then we are looping the outs. We are removing the overlapping boxes for the same instance. Then we are looping this indices, getting the left top width height. Then we are calculating the right and bottom of the box. Then we are appending final boxes dot append. Actually, we do not need to append this list. Instead, we can just use box cv2 dot rectangle frame top left bottom right, and it should be left and top. So this is the advantage when you overview your code after writing it. Okay, you find the mistakes that you have made while writing it. So this was it. Now if you look here, we have this YOLO models folder, and in that we have the face model and the hand model. Okay, let's import these models into our class Scots. Okay, so we'll write self dot face. Let's do it for face first, and then if it works, we'll do it for the hand. We'll give the pass here. Models face underscore model. So give it the directory here, and let's define the path. So dot face model cfg path equals to quest dot path dot join. Then in this we have the cfg file. We'll take this and we will do the same for weights path. Then we will call the YOLO model class here. YOLO model, and this will require the CFG file path and the weights file path. So we will just pass this. And now our model is loaded. Now in the class Scots, we will write one method to get the coordinates from the class YOLO model. Okay, get faces. And here, like faces equals to self dot face YOLO model dot detect objects, and here we'll pass, let's give the parameter image, and we'll pass the image here. Okay, now we will print faces, and we'll have to call this get faces in the capture and show. This is our main method. Okay, so let's call this here, and not just faces. In YOLO model, let's also return the image, because we are drawing the image, right? Final boxes, like we have to return the frame as well. Okay, and here we will return image, and with objects we will return image in the detect objects. Then here faces and then image, and then we will return the faces and image. So faces will be containing the list of the coordinates, and this image will be after drawing the bounding box, this function will return the image. Okay, but we'll have to call this image here. Sorry, we'll have to call this get faces here. Face coordinates comma image equals self dot get faces, and then we have to pass the image here. Okay, I think this should be sufficient. So let's run this. Okay, no, it's not properly detecting it. Might be some issue with the coordinates. So let's see what mistake we have done. Uh, yeah, I think we have to switch this right and then this bottom. Let's run it now. Yeah, awesome. Now it's being detected. Now our face is being detected. Let's see. We haven't written any code to detect our hands yet. Okay, so let's do that. Same way, we'll have to create another method to detect the hands. Let's copy this, paste it, and detect hands. Okay, now let's copy this also and this model and model. Just giving the path for the hand model. Model. Also, we could see the coordinates that we printed here in the faces. So move this, and let's call this here and coordinates image get hands. Now I think this should be sufficient and it should detect our hands and faces. So run this. Our hands and faces are being detected now by the model. So our code is working fine. Awesome. This looks good. So this was it in this video. See you in the next video. Thank you.